In this video, we're going to talk about Kp, the equilibrium constant to do with gases and homogeneous equilibrium. We're going to write expressions and calculate Kp. Now, you're used to Kc looking like this, products over reactants. Now, Kp is incredibly similar. Okay, so if we look at this, Kp is just with homogeneous equilibria, so everything must be a gas, absolutely everything. So, and it's exactly the same in terms of products over reactants. Everything must be in the same state, for example, and we put the partial pressures into the equation. Now, think of it like this. This is for the contact process. So the contact process says 2 here for SO2 and 1 for O2. So you can see here the SO2 is raised to the power of 2 and the O2 is not raised to the power. So it's exactly the same as Kc. You can also see that SO3 is raised to the power 2. Now you might ask yourself, why is there a P there? So the P is saying that these are partial pressures. And we'll explain what partial pressures are next. But basically you put the pressures into the equation just like before you put the concentrations into the equation. Now you put the pressures into the equation itself. But really important, everything is a gas and you're dealing with pressures. So how do we calculate the partial pressures? So partial pressure is equal, and in this case we can call it A, but the partial pressure is equal to a mole fraction of A, whatever A is, times the pressure. We're going to call the partial pressure P. Now, that basically means the partial pressure of A is equal to the mole fraction of A times the total pressure, which is big P. Okay, so basically the partial pressure is basically the different parts of the pressure that contribute to the whole pressure. So if you added all the partial pressures up together, it would equal the total pressure. But what we really need to do is do this mole fraction. Okay, and this mole fraction will allow us to calculate the partial pressures, and then obviously the sum of those will create our total pressure. Or the other way around, we can know our total pressure, know our mole fraction, and then calculate our partial pressures. But first of all, we need to know our mole fraction. So let's do our mole fraction first. So calculate the mole fraction of water and ethanoic acid, okay, in a mixture where there's 9 grams and there's 120 grams. So you can do mole fractions just from masses, okay, or you can do mole fractions from pressures essentially as well, because if everything is at the same pressure and same temperature, then the same number of moles occupies the same volume, you see. So, but anyway, let's do it in this way first. Okay, so all fractions should add up to 1. Let's put it to the side. Okay, and then let's look at how you do it. So all you do is this. Your mole fraction is going to be whatever your moles were. So for example, moles of H2O, okay, is going to be equal to your 9 grams, and your 9 grams we've got in the equation is going to be divided by 18 grams per mole. That is our MR, so mass over MR. 9 divided by 18 is 0.5 mole. Right, so we've got our moles of our water. Now we're going to do our moles, but this time of our acid, and it says ethanoic acid. Okay, so that's 120 grams. So there is our ethanoic acid, and we've got basically 120 grams, and we divide that by its relative, or its molecular mass, and its molecular mass is 60. Okay, so again, nothing to stop you doing this yourself. And then that will equal, if that's 0.5, this is going to be 2 moles. Okay? So that's not 0.5, that's going to be 2. Right. So we've got our number of moles. Now we need to do our mole fraction. So the total number of moles is 2.5. So total is 2.5 moles. So a mole fraction just takes each number of moles and divide it by the total. So we are going to go for our water. And our water is going to be 0.5 moles divided by the total, which is 2.5. Okay, which equals 0.2. We then go for our acid, okay, which is going to be 2 divided by 2.5, which is equal to 0.8. 0.8. So basically we have our mole fractions of these different components. Now what we're going to do is take it into a calculation of Kp and try and use these mole fractions. We're now going to move on to calculating Kp, and we're going to use the Haber process. And we can see they're all in the same state and they're all gases, so we can do Kp. And the question will ask you to calculate Kp anyway. Here's our total pressure. We can only use the units of our pressure to get our units for our Kp, but we'll talk about that in a little bit. And the mixture consists of these moles of the different parts. It's been nice to you and given you the moles. You might have to calculate the moles through masses, and that's just a mass over molecular mass, or you might have to get the moles from the fact that, remember, at the same temperature and pressure, the volume, if it's the same, has the same number of moles. So for example, if there's 10 centimeters cubed of this and 10 of this, that has the same number of moles as this. So if the total, for example, pressure is 200, okay, and the total pressure is 200, you know that's 50, that's 100, you know that has twice as many moles as this and this, for example. Okay, but we'll talk about that in another example. So if we then look at this, the units of partial pressure are given by the units of the total pressure. But like I said, we'll talk about that later. So let's now do the mole fractions before we can turn them into the partial pressure. So if you know already how to do this, do it. Okay, stop the video, make this a bit more active. Now, 20 divided by 100 equals 0.2. Okay, 100 is your total, 20 plus 60 plus 20. Okay, so 20 divided by 100 is 0.2. There's your mole fraction. Mole fraction is then times by the partial pressure. Partial pressure is 200 total pressure is 200, which is from the equation, and you get your partial pressure of 40. Now, if you do that all the way down, okay, and you can get the other two, and you can see I've just used the moles divided by the total moles, and then taken the mole fraction and times it by the total pressure to get partial pressures. Let's move this down and highlight the partial pressures again. I'm just going to do the Kp expression and calculate Kp and do the units. If you want to stop the video and do this, please do. Right, so Kp expression, really, really important. I'm going to do the Kp expression over here. So Kp is equal. So the first thing is partial pressures are shown by a P. Now, you might see in different places it might be PP or other notations with a P inside the brackets, but this one is the one that gets you a mark every time, so just use this one. A P is for partial pressure. Most important thing is round brackets, not square brackets, round brackets. Round brackets mean that you have a partial pressure. Square would mean you have a concentration. Now then we get the products, which is NH3. And then we look at the balancing in the equation, which is a 2. This is very much like Kc. It is just literally a Kc expression just for gases with pressures. And then we just go N2 in those nice brackets with a P times H2 in the nice brackets. But this time, look at the H2, it's got 3 by it. So I've got to put a 3 by it. And that's going to get me a mark in the exam. So even if you don't remember how to do it in the exam, but you know how to do the expression. Really, really important. Right, okay, so we've got our expression. All we need to do is put the numbers in, basically, that we've done. So that means Kp is going to be equal, we've got NH3 squared first. So there's our, and we're just going to put our numbers in, basically. So our partial pressure is going to be, let's look down here, let's look for our NH3. NH3 is 40. You don't really have to put the P in, you can just put 40, just put the numbers. I'm just showing you how I put the number in where the NH3 is. Okay, you could literally just put 40 squared. Right, okay, if that is the case, we then go N2, and we're looking at N2, we can see it's 40 as well. I'm not going to write the P this time because I just showed you that I put the number in. I'm just going to write the numbers. Right, and then from this point, H2 is 120. But again, we remember that this is cubed. Now, what I'm going to do is I'll do the units in the later section. So if we look here, 40 squared, put that into the calculator, and you will get 2.31 times 10 to the minus 5 to 3 significant figures. Remember, we always quote it to 3 significant figures unless we're asked to do something else or we're asked to do an appropriate number of significant figures. So I'm going to do it to 3. Now, if that is the case, we'll then look at this and we can do some units. So we can go ATM, and we know ATM is squared. And we can go ATM again, and we can go ATM, which is cubed. Okay, and we got the ATM from the equation up here. So that means, basically what we have is we are going to cancel that. Okay, and we're going to cancel out that one. We need to cancel out 2 of them. So we can get rid of that and turn it into a 2 because we've cancelled out one of them. That means I have ATM to the power 2. To get it up to the top, I need to raise it, times it by -1, which means basically it's ATM minus 2. Okay, so our final answer is 2.31 times 10 to the minus 5. Now let's look at it in terms of marks as well. You're going to get a mark for this working out here, you're going to get a mark for this unit here, and you're going to get a mark for that answer there to the right number of sig figs. So this is how you use mole fractions to calculate partial pressures, to calculate Kp, to give your units and your final answer. So we're now going to do an example with heterogeneous equilibria and do a Kp calculation. So we can see here, just to get you a bit of practice, can you do the expression for this reaction? Remember, it's products of reactants like Kc, but it's with partial pressures, and there's no solids or liquids are included in the expression. So if you can do it, please do it now. Now, the expression for the reaction above is this. So you can see our products over our reactants. You've got CO, which is a product here. You've got H2, which is another product here. You've got reactant, H2O, which is over there, and the C has been eliminated, so it's not there. Okay, and that will give you your overall expression. You're going to have to do that most often for heterogeneous equilibria. Now let's go and do a question. So this time we've got 1 mole of NO2 compressed to 200 kilopascals, which is the total pressure, and all the partial pressures add up to the total pressure. Now it's found at equilibrium, there's 0.2 of the NO2 remaining, and you've got here the equation here. So you've got 0.2 of this, okay, remaining. How much of that did you make? And we can do that through an ICE table. So let's move that to the side. And then let's do the first bit. So step 1, work out the mole fractions and use the balanced equation. So the balanced equation is here, so you've got 2 and N2O4, and we just got that from the balanced equation over there. You started off with 1 mole, so you see if I go up here, you can see 1 mole right here of NO2. So we've got 1 mole of NO2, and that's where we got it from. We found at equilibrium there's 0.2 moles of the NO2 remaining, so that 0.2 goes there. The difference between this is the change, which is 0.8. Now the ratio is 2 to 1. So if we take that 0.8 and we divide it by 2, we get 0.4 that we've produced of our product. Now, that is also the equilibrium amount. So we have got 2, essentially, amounts of moles here. Now we need to turn that into the mole fraction. So the mole fraction, okay, is going to be to take 0.2 divided by the total, which is 0.6, and there you've got your mole fraction. And then your 0.4 of the N2O4 divided by the total, which is 0.66. So we got that 0.6 just by adding the 0.2 and 0.4 together, and that is our total. Then we use the mole fractions to calculate the partial pressure. Again, you can do any of this. You can stop the video, you can do it yourself. Okay, and what we do is times those by the total pressure. The total pressure is 200, and it came in kilopascals. So therefore, 200 times 0.33, which is from there, is 66.6 kilopascals. And then for the N2O4, 0.66 times 200, which is 133 kilopascals. Again, we're going to use the whole number in the calculator, which is why we've got the 3 dots. Now, if that is the case, we can put that into the Kp expression. And we put that into the K expression here, the Kp expression here. That's because the balanced equation was NO2 is our reactant, so 2NO2, so therefore that's where you square. And that's where you take your NO2 partial pressure with 66.6. And then the N2O4 partial pressure is 133, or 133.33. And that goes on top because that's the product, and it's not raised to a power because there's only 1 molecule of it. And that is how you'd use the ICE tables to do a slightly more complex calculation using heterogeneous equilibria to calculate Kp. So we're now going to look at what happens to Kp when you change the temperature. And what you can use is the change in temperature and the effect on Kp to determine whether this is exothermic or endothermic. So let's have a look at that. So first of all, here is our Kp equation. You can see our Kp equation has our products squared versus H2 and I2, and you can see I've got that from the balanced equation. Now if we went over here and we say, look, the temperature has gone up and the Kp has gone down. So the Kp has gone down. So now what needs to happen for Kp to go down? That's the important thing. What needs to happen for Kp to go down? Well, for Kp to go down, the product, okay, has to decrease because this numerator has to become a smaller number, okay, than the denominator, okay, to make Kp a smaller number. So that has to decrease. Now that means the equilibrium in this case, when you increase the temperature, the equilibrium will shift to the left. So when you increase the temperature, it will shift to the left. Now, if I increase the temperature, according to Le Chatelier's, it will want to decrease the temperature. So it will want to follow the endothermic reaction. So I know when I'm increasing, let's just go back here again. So when I increase the temperature, I know that my concentration of my reactants, and therefore the partial pressure, will go down. That means the equilibrium must be going to the left. Now the response, according to Le Chatelier's, is when you increase the temperature, it's going to want to decrease, and the decreasing it is the endothermic reaction. So that means this is endothermic in the backwards direction and exothermic in the forward direction. Okay, now we'll go through that in a lot more detail when we do the exam style questions video, but for now we've got a bit of a summary. So if you look at the summary, effect of increasing temperature on equilibrium, if it's exothermic, the reaction, Kc and Kp will decrease when you increase the temperature. And the equilibrium will shift to the left, just like this. So this is an exothermic reaction. And I would write this out if I was you. I'd write this out, all the labels, all this kind of thing, and do that. Endothermic, if you increase the temperature, Kc and Kp will increase, and it will shift to the right. Okay, and you can see from this example, the temperature has gone up, but Kp has gone down. So we're definitely in this one here. We are exothermic. Now, you can either understand all of this, which I prefer, it's much better, or you can remember this nice summary table. And that is just a summary of the effects of increasing temperature on the equilibrium constant, whether it's Kc or Kp. And you'll go through exam style questions once you watch the exam style questions video.